Okay, today we will go into some basics, let's call, of numerical methods. And for this, we will start with the following. This is somehow working. First of all, what are the main properties of a numerical method? What do we expect? And what properties such a numerical method has to fulfill? That is a very important issue. We cannot go to all details, but the main properties I will try to explain to you. And then we will dig in, as you can see here, to the finite difference method. The finite difference method you already know. At least you had the ordinary differential equation in time, and you have done a discretization in time by simply approximating the time derivative by the value of the unknown at time t plus delta t minus the value at t divided by delta t. A very simple Euler formula, and the same you clearly can do in space. And we will look up for it, how you do it in space. So it is a method which is straightforward, not as, I would say, complicated, has quite some restrictions, but if you have simple geometries, it can be very fast and especially in electromagnetic wave propagation, very often used. A very general method you can use for any partial differential equation is clearly the finite element method. And we will see it is really a great method, but more involved when you look at the implementation codes for a finite difference scheme and for a finite element method. Well, it is quite different and it is much more involved, but it is really general and you can use it, let's say, for any partial differential equation, any complex geometry, and therefore it's really the method of choice, although not for each problem at hand it will be the most efficient one. Most efficient means, let's say, for some discretization to get the smallest error and being as fast as possible, because at the end we are not interested to wait for some weeks to get the solution. We hope to get it somehow within some hours, clearly depending on the mesh size you have. So I already told you a mesh, which means we have to discretize. So we cannot solve analytically, so we somehow have to discretize the computational domain. Okay, so let's dig in, and we will mainly focus here to the Laplace equation, as you know, and I will go to some details at the end of the course. We have quite a lot of special courses towards the finite element method for electromagnetics, but also other physical fields and coupled field problems, especially towards electromagnetics. So the main properties we are looking for is that the method has consistency, is stable, and we will see if these two are fulfilled, then it is equal that we have a convergence method. Convergence method, simply speaking, means when you refine and refine, so making your mesh size smaller and smaller, your discretization, you converge to the correct solution. And that is what we expect. Well, there will be some analysis necessary that we know how fast we converge, but let's make it simple and say, okay, I have a computational mesh, I refine it and see, at least when I have an analytical solution, that I converge to the true solution. Not easy, very often, what is the true solution? Because we have no analytical solution which we can compare with. And so it is very important, it's not our job, but the job of the mathematicians, that we know, okay, with this method with which we solve numerically the partial differential equation, let's say, for example, electromagnetic waves, so the full Maxwell's equation, we know that we get convergence when we refine our computational mesh. So let's start with the first topic, consistency. And for this, make it as follows. In mathematics, you mainly write the partial differential equation like this. L is our differential operator, could be the Laplace operator. Yeah, very simple speaking for us. Let's think of electrostatics. Yeah, we have minus the Laplacian of the scalar electric potential is equal to some charge density, let's say. Okay, so this is the differential operator. U, in our cases, we are still on the continuous level. I will always speak on the continuous level, where we have our analytical partial differential equation, and the discrete level where we already have applied our discretization method, our numerical method, like finite difference or finite. So U should be the exact solution, and clearly we have a right-hand side, RHS as you call it. This is for us the excitation. That could be, for example, the charge density we have within our computational domain. So you write this down. So I also write here simply that could be minus Laplacian of the scalar potential is equal to the charge density. And then clearly not written down, but we know you just get a unique solution when you also have correct boundary condition. So we have to know along the whole boundary our boundary condition. That could be a homogeneous or inhomogeneous directly boundary condition where we prescribe the electric potential to be grounded, meaning zero, or to have any value, for example. Okay, now when we do the discretization, our discretization parameter is h, which means we simply write down here our partial differential equation in the same way, but now instead of L, we have L subscribe H. And that means that is already a discretization we have performed. We are looking for a discrete solution, UH, yeah? And clearly also the right-hand side has to be approximated somehow. And that means, in this sense, that importing H is our discretization parameter. That is simply speaking, if you have, let's say here, such a very simple mesh, that this is the edge length of such an element, for example. Yeah? Now, clearly, if you have a very inconsistent mesh, meaning somewhere very fine, somewhere very large, then you will make and take out some average edge size you have within your discrete domain. Now, consistent mean, and now you see, I already write the numerical method is consistent if this property is fulfilled. So this double line always means a norm. It's not easy what is the appropriate norm, but for most cases, we just take the L2 norm. For everybody, it's clear what is the L2 norm, or do you like I write it explicitly? So I hope I have here. So I write it down in this sense. So we have the L2 mostly written in this form, L2 norm, and we have here UH, which is something, let's say U1, U2, U3 until UM. So we have discretized our domain, and at all the nodes we are searching for our unknown U. As you know, since a vector, I write it transposed. And the L2 norm of UH is nothing else as you take the sum over all your elements you have in the vector from 1 to m, ui squared, and then you put in front the number of entries you have, and you take the square root. So this is the simple norm. Yeah? And the L2 norm, and this is mainly used. Yeah? We will also have L1 norms, LP norms, where P could be not only here, P would be 2, therefore L2 norm, P could be 3, 4, could be infinity, L infinity norm. Do you know what is the L infinity norm? You take out of your vector the largest value, that is the infinity. So not as complex. Yeah? Okay, but let's restrict, especially in this course here, we take a simple L2. Okay, and you see when you have your discrete operator, yeah, multiplied, which will be our system matrix at the end. After the discretization, we get out of the Laplace operator a system matrix multiplied with the number of unknowns, UH, the unknowns at all the nodes. Yeah, I make here perhaps with red, these are the nodes, and in all these nodes, yeah, we want to have our physical quantity at these nodes. So that means system matrix multiplied with the vector of unknowns is a vector. Yeah? And you take the difference with the right hand side, also the discrete one. And this is smaller or equal, it's always the same case in mathematics what you do, a constant. And important would be or is that this constant is independent of your mesh size h. Yeah? That is important. And then you see it is the discretization parameter up to p. And so you see, when you make h smaller, so you divide it by 2, yeah, and you square it, you have 1 over 4. Yeah? And that you see that the finer the mesh, yeah, the smaller the error will be if this inequality is fulfilled. Yeah? So you see it is a sensible definition that the difference between your approximate operator, which gives you a system matrix with the vector of unknowns minus the discrete right hand side. Yeah? So an unbalance you have due to the discretization, because clearly if this would be in the continuous form, forget the h, that should be 0, because we have LU equal F. But this is not fulfilled when you do a discretization due to your discretization error. Yeah, and that this is smaller, somewhere a proportional factor discretization size with some exponent b, and in this sense we can also clearly, because we have here just considered space discretization, but as you know in electrodynamics especially, we also have the dependency on time. So then clearly you not only have to discretize in space, you also have to discretize in time, and therefore you have then this general expression, and that would be great if you really can do the analysis and get then such an inequality, and you know, okay, the convergence rate towards the space discretization is p, yeah, could be 2, or just 1 or 3, yeah, or it could be also exponential. Then you have a very optimal discretization. And you also see here the parameter q, and you know the order of consistency with respect to the time discretization. Okay, so these are clearly then jobs of mathematicians, not easy to get it. But anyway, you should just have seen how you define consistency, and even in a very general form where we have a dependency on space and time. Okay, so all what we should take away is we make the mesh finer, so the mesh size gets smaller, and our error we make, our numerical error, also gets smaller. That is important. On the other hand, we should also have stability, yeah, because we have some perturbation, as you know, since we do a numerical computation, we always can have small perturbation towards the data. For example, the discretization error or the rounding. Yeah, you have to round within a computer. You cannot represent exactly a value. And that means at the end that you fulfill such an equation that when you perturb a little bit your numerical solution, that still it will not explode. It will be a little bit different when it is not disturbed, this numerical solution, because as you see, again the norm, let's take the L2 norm, should be smaller or equal a constant. So it is not exploding. Do you think we also have stability problems for a continuous partial differential equation? So it is our analytical model. We have the partial differential equation. We have the boundary condition. Do you think you could also have their instabilities? Of course you can have, yeah. For most partial differential equation we don't have. But we have partial differential equation where we really have a problem with stability. And in order to get stability, we have to do something. You call this especially regularization. So you add some term in order to get a stable continuous partial differential equation. Mainly this can be due to material parameters. When you disturb a little bit the material parameters, you get a totally different solution. Yeah? So even on the continuous level, will be not our job, but on the continuous level, we have to be careful and should know at least this is a PDE which has instabilities. The instability could be a singularity. Do you know singularities in electromagnetics? Charges. Yeah, what about electrodes? At corners of electrodes. Yeah, you have a singularity there. Yeah, and correctly combined with the charges, you have an accumulation of the charges there. Yeah? When you have a simple setup, even a simple setup, yeah, like this, you have here the top electrode and the bottom electrode. Yeah? And you look how your charge distribution is, then the charge distribution is not constant along the electrode. Yeah? Along here, the bottom surface of this electrode. Yeah? You will see that you will have an accumulation of charges towards the corners here. Yeah? And it will be somehow constant here, but it will increase towards the corner. And actually the Laplace operator, because what we solve is a Laplace or Poisson equation for electrostatics, has a singularity within a corner. Yeah? So at the end, when you compute the energy, it's not a problem because you integrate over your computational domain, and this singularity you have in such a corner here, yeah, when you integrate over the volume, then this is somehow kept by the small volume, yeah, and it's not exploding your energy. But if you look at your electric field, for example, there you will see that you will have here the largest electric field, and it increases and increases when you make your mesh finer and finer. Yeah? Okay, so that's why we very often clearly look at energy values and not only at local physical quantities. Okay, so this is stability. Stability can even happen in the continuous space, but in the discrete space it mainly can happen. But nowadays, since we have such accurate computers, meaning you have 64-bit for the representation, it is not a big issue. Yeah, and in a standard case, there should be no problems. Anyway, if you perturbed your solution a little bit, yeah, that could be due to the rounding you have with the numerical representation of numbers. There should be a very small change to the solution. Otherwise, perhaps we have to look back to the continuous side of the partial differential equation if perhaps this is already unstable. Okay, now just summarizing here with a simple evaluation for the consistency is we take here the error norm, as we call, could be again the L2 norm, meaning the error between the analytic solution and the numerical solution, and that again should be smaller as our discretization parameter, and that is great if we can prove it with an exponent q, and q again is the order of convergence. Okay, so that again means making, simply speaking, making your mesh size smaller and smaller. You decrease your numerical error and converge to the analytic solution. And if you have consistency and stability, then we can say we have convergence. So convergence then really means making the mesh smaller and smaller, clearly increasing the computational time, but then we really converge to the correct solution. Okay, so these are some preliminary important properties we should have in mind. And for us, let's assume we have stability. Yeah, that is a very special issue, but we'd like to have also consistency, and that, just remind, means making the mesh finer and finer, meaning the number of unknowns are increasing and increasing, but that will give us an error, meaning any norm distance to the analytical solution, which is getting smaller and smaller. Okay, now as I have already told to you quite often, discretization. Discretization, as you can see here, mean you have a computational domain, and as you can see here, you subdivide it in small quadrilaterals. Yeah? And in these cases, you see, actually, we have this computational domain. I make this explicit because there is this part cut out. So this is the computational domain. Anyway, you make a computational mesh, not taking into account that this is, that this here is not the computational domain, because here this triangle is cut out. Yeah? So this is a possibility, but we have to take care that the blue one is actually our computational mesh. Another possibility is here B, and the possibility B is you still try to have quadrilaterals, meaning elements with 4 nodes, as you can see here, and you somehow are able that you really take into account that this triangle is cut out. But you see, you have very different elements here with different sizes. If this is good, we have to discuss. And then in part C, you see, you again have now very different sizes of the elements. And you even can have triangles combined with quadrilaterals, or in 3D, you even can combine hexahedra with tetrahedra, having pyramids, prism, everything. And that is a typical finite element mesh. And this, we will see, gives us not always the best property, but we will never have any problem in subdividing any complex geometry into finite elements, because in 2D with triangles this will be always possible. In 3D with stats this will be always possible. Although these elements will not have the best properties always will have quadrilaterals in 2D and hexahedra in 3D. Okay, so looking a little bit to the properties. So again, here our case A, so we see it is very easy when we look at this mesh, because each node, let's take out one of the nodes here, as you can see, has a constant number of neighbors. Yeah, clearly when you have a boundary node, it is different, but inside the domain, it's very easy, and to store this mesh can be very efficient. However, to approximate with such a regular mesh, yeah, we call it a regular mesh, here, this cutout of this triangle, you will always have a staircase. Yeah, so that means it will not be as accurate for any complex, even if you then have a curved surface. You always just can approximate it with staircases. You can make the approximation as good as possible, making the size of the elements smaller and smaller, because you use, as we call this, Cartesian grids. Cartesian grids is you subdivide your computational domain with a constant mesh size. And clearly, what you need then in your computational scheme is that you know which node really belongs to the computational domain like this, and clearly this is a node which doesn't belong. Yeah, so this you have to store. Yeah, because there you don't want to compute your unknown, because the boundary is this. Yeah, this is our boundary. So this part is not belonging to it. So you need some additional array, let's say, which stores, okay, you belong to the computational domain and you don't belong to it. So you see, making a Cartesian grid is easy. Yeah, but then this approximation at the surfaces is shown here, or even if you have a curved surface, let's say you discretize an electrical machine, well, that will be quite complicated. The second you call this, so you call this the Cartesian grid. The second one are these boundary twin grids. You still want to have, and that is necessary for the finite difference method, that you have in a regular node the same number of neighboring nodes. Yeah, we will just see. You need these trimmed meshes, and that is not easy, but for some cases you will be able, as you see, that all your elements are quadrilaterals. These are not these nicely straight quadrilaterals. They, as you see, are also curved and so on, but by some geometric mapping you obtain it, but clearly not for each geometry it will be possible. Yeah? And that is why the so-called unstructured grids come into play, and unstructured grids can be handled not efficiently with the finite difference method, forget it. For this, you need the finite element method. And this gives you the highest flexibility you ever can have for any complex geometry. Okay, so let's jump into our first method, the finite difference method. And that is, as I already told you, when you have a derivative of the unknown, start with one-dimensional problem, and it depends on the space coordinate x, can also depend on the time coordinate t. Then you do such approximation that you take the finite difference, yeah? Meaning you evaluate your unknown at x plus delta x minus the unknown at x divided by delta x. Yeah? Would be the same as we have here t plus delta t minus u evaluate at t divided by delta t. Yeah? So this is our standard approach, you know. And in order now to go at least to the two-dimensional case, it means that we have to do an approximation of the unknown depending on the two space coordinate x and y with respect to x. You mainly write it with a subscript x. That means you have to do the derivation with respect to x. Yeah, and it is quite the same as before. As you see, you let here the y constant. Yeah? And again, you have more or less the same formula. You evaluated x plus delta x, constant y, minus you evaluate u at x, constant y, divided by delta x. Yeah, and so you see we have such an approximation as we have here. We have the same if we do the derivative with respect to y. Now we know from the Laplace operator we need second spatial derivative, and this is done in this formula in order to get second order accuracy. So you see, you need, when you have the discretization, you need for the central point the two neighboring points. Let's say this is the x direction, this is the central point. We need then x minus delta x, and we need x plus delta x. Okay, and the same, as you can see, is here, where we have the derivative with respect to y. So we evaluate, and now already written with the index. Yeah, I should say to you the index I plus 1 means x plus delta x. Yeah, but we use the index simply because we will name all the nodes in the computational mesh, and so you see you will need straightforward the nodes on the left side and on the right side. If this is the x coordinate, if this is the y coordinate, you again need the upper and the lower value in order to do this approximation. And the nice thing is you are accurate up to second order. So it's not only first order, it's really second order. Okay, so that means now let's plug in what we just have discussed. We have seen how we do the space discretization of first order and of second order, and it's no difference if you take it in y or in x direction as we have seen it. And what we will now use is our standard equation here of the Laplace operator on the left-hand side, so the second space derivative with respect to x plus the second space derivative with respect to y is equal to f. So we know this is our simple Laplace operator. Delta u is equal to f. Okay, so step one is we need a computational mesh. So we subdivide our computational domain into rectangulars. So it's not necessary that the mesh size in x and in y direction is the same. And so in a simple case, let's say we have a constant delta x. It is not necessary that this discretization in x direction is always the same. It could be also a little bit different going on with the x coordinate, and the same holds true for the y coordinate. Now, let's plug in what we already have discussed. Yeah? If we go back, we have discussed how we do the second order discretization. Yeah? And here it makes sense with this indices I and j. So if you plug it in, nothing additional. We have this part here and we have this part. So the second space derivative with respect to x is now, due to this finite difference scheme, this term here in the denominator delta x squared. We use a constant delta x. Now it's easier, yeah. Otherwise, okay, you have to check. And there will be also an index for delta x squared. And we have it here, the second space derivative with respect to y. And clearly this has to be equal to the discrete value at ij of our source term. So we can even call this a so-called 5-point stencil. Please have a look here. Yeah? So this is your central node. And in order to do this discretization, as I have told you, you need in y direction not only j, you need j plus 1 and j minus 1. And in x direction, you have here at this node I, on the left side, you also need the unknown, or could be also the known. If it is on the boundary, we will differ between boundary and inner nodes. I minus 1, and you need I plus 1. Yeah? So in any inner node of the computational domain, this is your standard stencil. It is called 5-point stencil. And in order to get here this approximation for a node ij, you also need I minus 1, I plus 1, j minus 1, and j plus 1. So let's have it concrete. We have the following. We have 4 values for j, 1, 2, 3, 4, and the same, or sorry, I started with index 0. Always be a little bit careful if you use C++ or MATLAB or Python. Yeah, in MATLAB, the indices start with 1. Okay, so I started here, as you see, with 0. So j is going from 0 to 4, and the same I is going from 0 to 4. And we assume here, and that is why I put it in red, that all these nodes here are boundary nodes. Which means at these nodes we already know the solution. So these are boundary nodes, which means solution is known. Okay, so on the other hand, this means that the blue one are the unknowns. We don't know. And as we see, according to our computational mesh, these are 3 by 3, meaning 9 unknowns in this very small computational mesh. Okay, now when we go here, as you can see, in a first case, and now sort the finite difference equation for I equal 1 to capital I minus 1 and j equal 1 to capital J minus 1. That means these are the inner nodes. Yeah? And we assume that we have these boundary conditions. Yeah? As you see, at any constant x coordinate A, any constant x coordinate B, any constant y coordinate C, and y coordinate D, we have prescribed values. We call it UA, UB, UC, UD. Yeah? And that means really along these red nodes, we know the value. Yeah? Okay, so full boundary is a directly boundary where we already know our unknown U by UA, UB, UC, and UD. Okay, so in general, we can write down this equation here. Yeah? This is just a rearrangement of this equation here. Yeah? This is our general equation, and we now have to take care if there are also some boundary nodes included, and then we have to put these nodes to the right-hand side of our discrete equation because we know it already. It's not more any unknown. Okay, so you see we have a term 1 over delta x squared with ui minus 1 and j. We have a term at ui and j. Yeah, this is a mixing term where we have 1 over delta x squared, 1 over delta y squared. We have a term ui plus 1 and j, and the term ui j minus 1, and the term ui j plus 1. Yeah? So the central term is ij, yeah, which is here, we have terms towards the x coordinates which are on the left and which are on the right. And the same we have for y, yeah, this is the central term for j, sorry, and we have a j minus 1 and the j plus 1. So just an expansion of this equation here, nothing else, if you look. Yeah, it's just an expansion, and single write it for the different indices ij, I minus 1j, I plus 1j, I j minus 1, ij plus 1. Okay, now let's have a look to the grid points on the left boundary. Yeah, because on the left boundary we have the index I index 0 and j is just going on from 0 to 4 as we know, and along this boundary we know that this is already a constant value. We call it UA because it's a directly boundary condition. Now, if we are in such a sense, yeah, then let's have a look, for example, to this node here, yeah, and you know we take a stencil, yeah, a stencil means we take this node here, this node, we need this node and this node, but this node and this node is known, yeah, so there is no difference if this is, we take this node, yeah, so then this equation is our equation. But if it is this node here, where I and j is equal to 1, then the stencil tells us that we need this node, or the position of the unknown at this node, this node, this node, this node, to get this stencil at this ij. But this and this is known. Yeah? So we just take this out from the left-hand side and put it like a source term to the right-hand side because we know it. And that is done as shown here. And so you see on the right-hand side what pops up is exactly what we have here. Yeah? Because this part is actually known and we can take it. If, as you see, I is equal 1 and take care, for this case, I is equal 1, which means, yeah, that it is, yeah. So I is equal 1, so it is this part here. And j, take care, and j is 2 to j minus 2, which means just, I should take the unknowns, sorry. So this can be just this node here. As you see in our case, this can be just this node. Yeah? So if I this node here, yeah? And then this is the only boundary node, yeah? Because the other, not the others, perhaps we should take another value here, because the others will be here, here, and here. Okay, so you see this, the green one are unknowns, the blue one is our central node where we write down the equation, and the red one we know, yeah, and therefore you have u0, yeah, I is 0, and j is going, as you see, from 2 to j minus 1, which can be just 2 because j is 4, yeah. So this is such a node. However, it can be also the node for I and j equal 1. So I hope you allow me to now clean this. That means now I'm looking at this node here. Yeah? But for this node, as we know, this and this node we need in our stencil are known. Yeah? So this is, I take it this one. So what is just unknown, still unknown, again make it in green, is this here and this here, which means we now should have two terms we put on the right hand side. Yeah? And if you look here, you see it exactly. It is U01, exactly this node, and it is U10, U1 and j equals 0. These are these two nodes. Okay? So it is just a rearrangement of your equation. Yeah? So if we go back, we take our general equation. The general equation is this one here. And then we have to check which of our unknowns are knowns because they are on the boundary. Yeah? The boundary meaning, as we have discussed here, all these red nodes. Yeah? So if we have here any value on such a red node, we just put it on the right hand side. So this is the rearrangement we have to do. So we have seen we have a simple approximation. We directly approximate the Laplace operator, get this general equation, and the real work is just rearranging each equation for each of the nodes here, the blue one, because these are the unknowns, that some of them have boundary nodes. Yeah? And for these boundary nodes, we know already the solution, so we put it to the right-hand side, and that means the rearrangement. If we have done this, in our case, yeah, I go back because here I have nicely shown it, we will then have at the end, in this case, 9 equations. And if you look here, all of these 9 equations, we just have one equation where we have to do no rearrangement. This is this center node here. Yeah? For these nodes here, we always have involved some boundary nodes, yeah? Where we know the solution. Yeah? So for this equation, we have to do the rearrangement for 8 equations, and for one equation, no rearrangement, because the discretization includes an equation with all unknowns. That means at the end, what we get out is a system matrix A multiplied by the number, by a vector collecting the number of the unknowns. In our case, this is 9. The system matrix, we therefore will have a 9 by 9 system matrix. And we have a right-hand side, which not only includes our source term, let's say the charge density, but also includes values from the boundary where we know already the solution. Yeah? And this is then our solution vector, in our case going from 1 to 9, because we have these 9 unknowns. Yeah, and this system of equation, you need the algebraic solver. Yeah, and having this algebraic solver, then at hand, you get the solution. A direct solver, for example, or any iterative solver, and at the end, you get the solution with, again, I show it for these nodes here, yeah, which are the nodes, in our case, where we don't know in advance the solution. At the red nodes, we know already the solution because these are our directly boundary values along the outer surface, which is in 2D just a line. Okay, so what we have seen here in this sense is you have a straightforward approximation of your differential operator, in this case the Laplace operator, and the only work you have to do is this rearrangement, because you also have boundary nodes. Yeah? Clearly, this is now a simple case. For a practical problem, you will have a lot of unknowns and just some few nodes on the boundary where you know the value and where you need then to do these rearrangements. Yeah, here a simple example that you also see a practical solution. We have the following. electrostatic problem where we have an electrode here, two small electrodes here, and again such an electrode here. And as you can see here, along this line, we apply a potential of 2 volt. Along this line, a potential of 10 volt. So we have a nice potential difference. We should get out a nice electric field. And along these two small nodes, we have grounded. So the potential is equal to 0. Yeah, you see, we have no charge density. We have some prescribed values of the potential. So this is our simple Laplace equation for the electric potential V. We have here this boundary condition. Yeah? V at x equals 0 is exactly along this line, is 2 volt. And this is copy and paste. This should be 200. As you see, the space coordinate here is 200. Could be millimeter or centimeter or meter. It's up to us. But at x position 200 and y, it means it is this line, it is equal to 10 volt. And then we have, as you see, at the x position 50 and from 0 till 50, you again see here, this is y0 till 50. We have 0 and v at x position 50, and from 150 to 200, y coordinate, we also have 0. So this is the definition. We have our boundary condition, we have our Laplace operator, our Laplace equation here for the electrostatic field, and we can solve it now with the finite difference method. What you can see here, we can nicely do such a discretization of equal spaced elements here, and we have to clearly check here that along this line we know the boundary condition, and along these two small one. What do you think we will have along this outer boundary line and along this outer boundary line? What boundary condition you would apply? Yes, exactly. And we will put homogeneous Neumann. Yeah, homogeneous Neumann, I just go here. So so we will have homogeneous Neumann. Yeah, as we know, homogeneous Neumann somehow means the normal derivative with a normal derivative is equal to 0. To be precise, it is actually the flux, and the flux is correctly with epsilon 0 or any epsilon. Let's write any epsilon. It could have a value different from epsilon 0. You can have a dielectric material where you also have a relative permittivity. And you know what this actual is. Which physical value this is. We have two physical field quantities in the electrostatic field. We have the electric field strength itself, E, and the second one, it's D, the electric displacement. Yeah, and don't forget, D is simply epsilon E. Yeah, now speaking simply, this one, and we know we can write this as minus epsilon gradient of the scalar potential. Yeah, And now if you take the normal vector, so dot product with the normal vector, then you have n in D is equal to minus epsilon, and the gradient of a scalar dot product with the normal vector is the normal derivative. Yeah? So it is dv dn as I write it. Yeah? So actually that means that the normal component, we can also write it dn is equal to 0, which means the flux cannot go out of the domain. It has to be somehow parallel along the computational domain. Yeah? Which means also here, and that makes sense from the physical point of view, that the flux lines will be here in parallel. Yeah? Because the normal vector, for example, here the normal vector is going in this direction. Yeah? And the normal component of D is equal to 0, which means we will have flux lines which will go tangential here. Yeah? And clearly, the larger you make your computational domain, the smaller the error you make from the physical point of view. But somewhere you have to limit it. Yeah? And therefore, you, in this case, we immediately limit it along these two lines here, a homogeneous Neumann boundary condition. Sorry, here, exactly. Okay, so we have everything. That is what I have written here. And the normal vector is in y or minus y direction. Therefore, I have written it here for y equals 0 and y equal 200. Yeah, I go back. So y equals 0 will belong here, and y equal 200 will belong this line. Yeah, and the normal vector is in minus y direction or in plus y direction. Yeah, as we see here. So unit vector in y direction plus minus. Okay, so the discretization clearly for this first order, you know, we always write the derivative with respect to this index then can be simply written with this part. Yeah? And this is equal to 0, or we also have it at the position y equal 200, and we have it like this. Yeah. So in this sense, we get here also these values, which are then 0 within our stencil when we set up the equations. So looking to a very coarse mesh, as shown here, yeah, then clearly we can make again in blue what are the unknowns. Yeah, so that will be at this node, this node, this node, this node, this node. Take care also at these nodes, because at these nodes we know that the normal derivative is 0, but we don't know what is the value of the scalar potential itself. Yeah, we just know dv dy being equal to 0. Okay, and all the others we have there, we know the Dirichlet values, and we also have to plug it in and do this rearrangement of our equation. Yeah? So again, let's have a look. The Neumann boundary condition, perhaps we should make it in this sense, Neumann boundary condition. That's also known as Neumann. Then we make it in green. Yeah? So also here a green one. So this will be 2, 4, 5, 26, 28, 29. Yeah, hopefully this is also written on the slides as shown here. And the Dirichlet boundary conditions, now again, it was as we had before in red. So these are the Dirichlet points. and we know this is this point, this point, this point, this point, this point, these 2 points, and these points. So again, for this coarse grid, I have then a solution for a quite fine mesh in order to nicely see the electric field or the electric potential distribution, but to directly separate the nodes where we have to compute our electric scalar potential, the nodes where the Dirichlet boundary conditions are known, so we directly know what is the value of the electric scalar potential, and the Neumann boundary points where we know the normal derivative of the potential, but the potential itself we don't know. So it is, in this case, also unknowns. So also this, I have to write unknowns, and clearly also my blue one, also unknowns. Okay, yeah, and so you see, I would even say a MATLAB code is not as complicated, or a Python code. The main point is just this rearrangement, that you know at which point you have which boundary condition, and then correct your standard stencil as we have seen, and put all what is known to the right hand side. So this is the solution, what you see here, of a very fine computational grid. It is the following, as you can see, it is the electric scalar potential between 0 and 10. 10 was along this line here. 0, be careful, was this line here. And 2 volt was along this line. Perhaps one can imagine that here about this is 2 volt. And you get this distribution. From this solution, you can also do and compute this derivative. Again, you have to do a numerical derivation, which reduces clearly the accuracy, but that is necessary for any method, numerical method, when you compute out of your primary solution, in our case, the scalar electric potential, you compute out then, for example, the electric field. You have to take then the derivative with respect to x to get x component, and the derivative with respect to y to get the y component. Okay. Any questions concerning? Okay, I have not checked fully the chat. Should the approximation be? Okay. Have I made a mistake? I guess it was at this part here. Yeah, but it is of second order. The accuracy is of second order, is written here. This O means order. Yeah, this is this special O that means of second order. So delta x squared as well as delta y squared. Now I think, yeah, you always write it in this sense. Perhaps you mean this delta x squared. Yeah. So it is not delta of x squared, it is delta x squared as we have written here. Yeah, this is a standard notation, you write it. But to be precise, perhaps it's better you write it in this way. Okay? Okay, that was the question. I hope I could answer it. Any other question? Yeah. In a computation, yeah. So if we look.
Please repeat the question. It was not.
Yes, we will repeat the question. Yeah. So the question was, how do we include the Neumann boundary condition in this sense. So if we go back to this stencil we have here, you do not see that we have a first order. Yeah, we just have second order. And when we go here, then this would be the approximation. Yeah. In our case, since it is 0, we don't have to do anything. Yeah. If this has a value, then we have to rewrite here our part, where I am, as shown here. Yeah, as shown here, we have to rewrite it in this way, and instead of this stencil, we have 2 times this stencil here. Yeah, and then you can incorporate it. And that you have to do if it is different from 0, if it is inhomogeneous. Yeah? Because a second spatial derivative is nothing else as a first spatial derivative, and then again apply a spatial derivative of second order. In this case, you can incorporate it. So you have to rewrite, so this nice stencil have to be rewritten by 2 first order, yeah? Where we have a first order and apply on this first order again a finite difference approximation. In this case, since it is 0, we don't have to do anything. That's the nice thing. Yeah? But clearly, we can also have inhomogeneous, which is the case. Where do you think we have inhomogeneous, Neumann? From the physical point. Very good question that you raised it up. Sorry? No, let's keep electrostatics. We keep at the electrostatic field equation we just discussed. Perhaps I go to the slides here. Yeah. What is something like the, yeah. Yeah, but let's think physically. Which kind of charges do we have? Yes, exactly. This would be surface. That would be something like a surface charge. Yeah. So this this value we have here then would be not 0, but would be any value of a surface charge. Yeah. So that comes in naturally then. Yeah. A surface charge density. Yeah. Okay. So as you see, standard is that this is 0, meaning that the flux lines we have there, our field lines, will be along the tangential plane of our computational domain. They don't go out of the domain. Yeah? But very good, we could also have there some surface charge. Yeah? And that is if you have a charged electrode. Yeah? And we don't put a potential difference between top and bottom electrode. If, let's say, we have bottom electrode to be grounded, but the top electrode, we prescribe there a surface charge. Yeah? Exactly, and then this has to come in, and it will again give you some values on the right-hand side of your discrete equations. Okay, any further question? You will also have exercises on this and also on the finite element method, and hopefully you get a little bit into these parts. And as I have told you, to go really deeper, especially for the finite element method, because this is the method of choice for computational electromagnetics. We have our own courses where we are happy if you take part of in such courses. Okay, so before we stop, just a small jump in of the finite element method, that you now really see how different the finite element method is compared to the finite difference. I think the only challenge, as we have seen, is this incorporation of the boundary condition in the finite difference method. The other part is just straightforward, as we have seen. So the finite element method is really different, because for the finite element method, we don't discretize our partial differential equation. You call it also the strong form of the partial differential equation, which means the partial differential equation, boundary condition, and if we have time dependency, initial condition. No, we first go over to the weak, sometimes called variational form of the partial differential equation. What this is, we will just see in a minute. Yeah, and then for most cases, also this weak form will not be able to be solved. But important is that here, between these two formulations, there is an equal. There is no approximation. They are from an analytical point totally the same and should give the same solution if we are able to get the analytic solution. However, also this transformed formulation, let's call it, this weak formulation, in most cases, we are not able to solve it, and therefore we need an approximation, and we will use the Galerkin's approximation, which I will also show you in a minute, and or that we will see next. Okay, so the steps we have to do. We first transform the partial differential equation with the boundary conditions into the weak form. We then discretize the computational domain, which we have done also by the finite difference method. So the first step is a special step we didn't have within the finite difference method. Then we apply the Galerkin's method. So we also will approximate somehow, but now with so-called finite element basis function, with some interpolation functions, sometimes called shape functions, our unknowns. Yeah, we will make an ansatz with the approximation of the continuous unknowns, like our electric scalar potential, plug it into the weak formulation, and we will get out the algebraic system of equation, which we have to solve. And that, when we solve it, then again, as for the finite difference method, at all the nodes where our physical quantity, like the electric scalar potential, is unknown, we get the solution at this node, but just at this node. Yeah? Actually, we have no information what the solution is somewhere inside the element. We just get it at the finite element. The same as we had at the nodes when we did the finite difference approximation. And it's also the same. Yeah? It's not Shannon theorem, but it's also very similar as you do an analog digital conversion, where we also don't actually know what is our measurement signal between two digital values after the time discretization, yeah? After the conversion from the analog signal to the digital. Okay, and for this, what does this mean to go over to a weak formulation? Okay, so to be very precise in this sense, because this is one of the big power we have within the finite element method, actually we have such a partial differential equation. And this new, the material parameter, could be the permittivity, could be permeability, could be conductivity, whatever equation we have. But important is that in most cases, these material parameters depend on space. Perhaps they are constant in subdomain 1 and constant in subdomain 2, but at the interface, they immediately jump. As we know, we have a conductivity, electroconductivity in iron or copper. In air, it is 0. So you even could have a jump to 0. And that is a problem because, as you know, as you see here, we have the divergence material parameter gradient of the unknown. Yeah? So the unknown could be again our electric scalar potential, and the material parameter here could be the permittivity. And that is different in air as in a dielectric material. And the divergence is a space operator. How do you apply such a space operator on a material jumping parameter? Okay, you would have the delta function, but it will not really help. So you need, again, some approximation, or you can do it exact. with the finite element method in this sense. We have just again our more or less Laplace operator. We can have Dirichlet and Neumann homogeneous or inhomogeneous boundary conditions. And now the trick is as follows. We introduce a test function v with a scalar unknown, so the test function is also a scalar. And what you see, we multiply it with the partial differential equation and integrate over the computational domain. And that clearly should be 0. We also have in the strong form here that this is equal to 0. Okay, so this is clearly allowed. We multiply the partial differential equation with a test function and integrate over the computational domain. It clearly makes sense. Currently, we don't see any benefit, but that will come up soon. And this material parameter, gradient of the unknown, is any vector f. Yeah, why I put here this vector f? It's easier. You will see what we will apply here. We will apply the divergence theorem. We know that the volume integral of the divergence of a vector can be rewritten as a closed surface integral. Okay, however, we also be careful. We have also a scalar function, our test function here. Therefore, we will include it in the divergence, and we know that the divergence of a vector which is scaled by a scalar is the gradient of this scalar dot product with the vector plus the scalar divergence of this vector. Yeah, that is just expanding using the product rule. And now we see that this term, what we have here, so the scalar multiplied by the divergence of this vector, we also have here. Yeah? So we have the divergence of the vector, and here's the scalar. And that can be rewritten by the divergence of the product minus the gradient of v dot product with the vector, which means that exactly this term gives you now the material parameter depending on space, the gradient of the test function dot product with the gradient of the unknown, minus the divergence of this part here. I have just written it explicitly, where we have the test function, we have material parameter, and the gradient of u. Yeah, the gradient of u multiplied with the material parameter was our vector f. And that has to be equal to 0. And now, clearly, and that is the nice thing, we can expand this term here by the divergence theorem. Yeah? So instead of the divergence of this whole part here, we can rewrite this as a surface integral, as written here. Yeah? And what is the difference between this term we have obtained by multiplying this test function, integrating over the domain, and this expression here? A big and two important things we see. First of all, the material parameter gets rid of any spatial derivative. So we will have no problems of space-dependent material parameters, of jumping material parameters between subdomains. And, yeah, so this is very important that we see this. And when you look carefully, we have the gradient of u, we have the gradient of u. So we just have a first order spatial derivative. Yeah? This is the important part, what we have here in this sense, and not a second order derivative, which we had here. Yeah? Here, divergence, material parameter, gradient of the unknown, which means you can already approximate such a continuous unknown u, scalar electric potential, by any linear function, which is not possible in this case where we have the strong form or where we have this relation here, because second order derivative of a linear function as an approximation, for example, for this unknown will be 0. Okay, so two main points we have gained. And clearly what you also see here is we can now rewrite our surface term by a term over the Dirichlet boundary and the term over Neumann boundary. And nicely what you see, we will choose the test function to be 0 on the Dirichlet boundary condition. We are not interested in the solution of our unknown u on the Dirichlet boundary, we know it already. Yeah? So you will take v equals 0, which means this cancels out, and because v is equal to 0. And the second boundary integral we know, because the material parameter gradient u in n is our Neumann boundary condition. So you can incorporate the Neumann boundary condition in your formulation. You know this term and you can put it on the right hand. And that is then this important value here, where we still search for the unknown u, which fulfills some Dirichlet boundary conditions, but we know our value there at the Dirichlet boundary condition. And we have to solve this equation here, where I already have substituted the Neumann, inhomogeneous Neumann boundary by Qn. Yeah? So I just go back. That was this Qn. Yeah? Okay, so you nicely see a Neumann boundary condition you can incorporate in this weak formulation. The Dirichlet you have in addition to be forced on your solution, but it is something we know. Yeah, it is why we set the test function equal to 0. Okay, I think it's now a good time to stop. I'm already 2 times over. 2 minutes, not 2 times, 2 minutes over.